All right, these are the notes for the first part of section 2.4 for pre-calculus. We are looking at how do we find zeros of our polynomial functions. So in our last couple sections, we looked at the shape of different polynomials and interpreting graphs. Now we're going to look at how we find those zeros. So our objectives today, we're going to review how do we do long division with polynomials and what does that division algorithm look like. We're going to also look at the remainder and factor theorems. And in order to do some of those things, we're going to also look at another type of division, that's synthetic division. So just a quick review, how do we divide just regular numbers without a calculator? And some of the terms. So the number in front here, the 32, is our divisor. The dividend is the 3,587. And what we get on top is our quotient, the answer. And what we have at the bottom is the remainder. Okay, so it might have been written originally like this. Okay. First thing we do is we look at the 32. Does 32 go into 3? No. So then we have to move over. Does 32 go into 35? Yes, it would go in once. We then put that answer down there, 1 times 32, and then we subtract. What we have left is a 3. And then our next step is to bring down our 8. All right, we bring down our 8 and we divide again. 32 goes into 38 once. We have 32, subtracting, we have 6. And then we bring down our 7 and we try it again. 32 goes into 67 twice. 2 times 32 is 64. And when we subtract, we end up with a 3. And that would be our remainder. So we could write that and say that 3,587 divided by 32 is 112. And then when you first started learning division, you would just write R3, remainder 3. But then you learned that that's really a fraction. We have 3 out of 32 left over. So we have 112 and 3/32. Now we can take that same division idea, those same steps, and use it with polynomials. So you might see the same numbers here, right? 3,587, we're dividing by 32. But in this time, we have variables attached. So we're going to put our 3x plus 2 outside. Inside, we have 3x cubed plus 5x squared plus 8x plus 7. And one thing to remember with division, whether it's long division or synthetic, if you have any terms that are missing, you do need to put a 0 in there to hold that spot. It's kind of like saying if we're going to divide 302, we wouldn't just write the 3 and the 2. We need that 0 in there. All right. So for polynomial division, we focus on just the first term in each one. Okay, so if we have 3x cubed and we're dividing by 3x, what do we have left over? That would simply be an x squared. That's what goes on top. And then we take that x squared times the 3x plus 2 in front, which gives us 3x cubed plus 2x squared, and that's what goes underneath. So 3x cubed plus 2x squared. And then if you remember the steps, our next step is to subtract, but we want to subtract that whole thing. Okay? The first term should always drop out or you didn't do it right. So 3x cubed divided by 3x cubed is gone. Or sorry, 3x cubed minus 3x cubed is gone. 5x squared minus 2x squared leaves us 3x squareds. And then we bring down our next term, which is our 8x. And we just keep repeating this process. All right, so 3x squared, focus on the first piece, and we're dividing by the first piece of this, the 3x, and all we would have left would be an x. So that's going to go up here, a positive x. And then I take x times 3x plus 2, which gets me 3x squared plus 2x, and now I have to subtract that. Again, the first term drops out. 3x squared minus 3x squared is 0. 8x minus 2x gives me 6x, and I bring down my 7. and repeat it again. I'm taking 6x, my first term, divided by my first term, 3x, which is just a 2, and then multiply 2 times all of that, gets me 6x plus 4, and I subtract. So 6x minus 6x is gone, 7 minus 4 is 3. So you'll see the same kind of numbers that we had in the original problem. So I would say that if I am taking 3x cubed plus 5x squared plus 8x plus 7, and I'm dividing by 3x plus 2, my answer came out to be what I had on top, x squared plus x plus 2, and then this is my remainder, and I was dividing by 3x plus 2. Okay? That's considered fraction form for our answer. All right, we can check our results. If we take our divisor times our quotient and add back in the remainder, we should get our dividend, okay, what we started with. It says check this with the two division problems from the former page. So if we go back, our first question was 3,587 divided by 32, and we said our answer was 112 and 3/32 was our remainder piece. Okay, so what this is saying is I should be able to multiply 32 times the 112 and add back in the extra 3 that I had as a remainder, and you can try that with your calculators. You should get back to your original dividends, 3,587. Okay, and we can check that with our polynomial one as well. All right, we should be able to take our divisor, 3x plus 2, multiply to the quotient that we got, x squared plus x plus 2, and then add back in our remainder. And it should give us back what we started with. So if we distribute all of this, we've got 3x cubed plus 3x squared plus 6x. We have another 2x squared, 2x, and 4, plus the 3 remainder. Combining all those like terms, we end up with 3x cubed plus 5x squared plus 8x plus 7, which again was our original dividend. So it is possible to check your work. Obviously it's extra steps, but if it was a test question, I would certainly do that. So that's what we're seeing right here, this division algorithm. Okay? It says if we take our function, our polynomial, we should be able to take our divisor times our quotient and add back in our remainder, and we get back where we started. Okay? Keep in mind that with division, you are always dividing until the remainder is of a smaller degree. So think back to, let's look back at that first page. Okay? Our remainder here, 3, we could not divide a 32 out of it. It was too small. Okay? With polynomials, the same idea. Our divisor was linear, right? 3x plus 2 was degree 1, and we look at our remainder, it's degree 0. So it has to be a smaller degree. If we had any x's still left here in the remainder, we wouldn't be finished. We'd still need to divide further. All right. So it says f of x in the division algorithm is your dividend, and d of x is your divisor. If the remainder is 0, we say that d of x divides evenly into f of x. Okay. The summary statement in the division algorithm will sometimes be written in fraction form. Okay, so again, we take our original dividend, we're dividing by d of x, we get our quotient plus the remainder piece that's being divided by that divisor. It's just that it's too small to reduce that any further. Okay? So once again, this is how we had written that first example. Okay? This is our quotient, what you saw on the top of the whole question as we worked through, and this was our remainder. Okay? All right. Example 1. It says use long division to find the quotient and remainder when 2x to the fourth minus x cubed minus 2 is divided by 2x squared plus x plus 1. It says to write your summary statement in both polynomial and fraction form. All right, so let's set this up. We have our divisor is 2x. Let me get a smaller font here. 2x squared plus x plus 1. Notice we aren't missing any terms that we would need zeros on that one. But our dividend, we do. We have 2x to the fourth. We have a negative x cubed. And then we don't have any x squareds. We don't have any x's, but we have a constant of negative 2. So it is important that we hold those place values with zeros for any missing terms. All right, once again, we focus on the first term in each polynomial. So we're taking 2x to the fourth, we're dividing out 2x squared. All right, 2x to the fourth divided by 2x squared just leaves us an x squared. That's what goes up on top. Then we multiply x squared to the whole divisor. So x squared times 2x squared would be 2x to the fourth. X squared times x is x cubed. X squared times 1 is x squared. And then we have to subtract. And this is the step where most people make mistakes with that subtraction, so take your time. We have 2x to the fourth minus 2x to the fourth. That disappears. We have negative x cubed, and we're subtracting an x cubed, so we now have negative 2x cubes. We had no x squareds, but we're subtracting 1, so we have negative 1x squared. And then we would bring down our next term, which in this case is just 0x. Okay? And then we repeat that process again. So we're going to take the first term again, divided by our first term, which should leave us with a negative x left over. Right? And that goes on top. And then we multiply the whole thing. So negative x squared times 2x, negative x times 2x squared would be negative 2x cubed. Negative x times x is negative x squared. Negative x times 1 is negative x. And then we subtract. Our first term drops out again. We have negative x squared minus a negative x squared, which is going to drop out as well. Then we have 0x minus a negative x, which leaves us 1x. And then we bring down our next term, which is a negative 2. But now notice that our degree here is a 1, and that is smaller than our degree of our divisor. So we're done. We can't take any x squareds out of just an x. Okay? So they've asked us to write this in two different forms, in polynomial form and in fractional form. Okay? So as a polynomial, we would say 2x to the fourth minus x cubed minus 2, that original dividend, could be found by taking our divisor, 2x squared plus x plus 1, multiply it to our quotient, the answer we just got, which is what we had on top here, x squared minus x. And then we should be able to add in our remainder here, which is x minus 2. Okay, that's polynomial form. And if you actually FOILed or multiplied everything out, combined like terms, you should get back to this 2x to the fourth minus x cubed minus 2. In fraction form, we are saying, let's move this out of the way here. 2x to the fourth minus x cubed minus 2, our dividend. We're dividing it by 2x squared plus x plus 1. The answer we got out was x squared minus x, but we had a remainder. That remainder was x minus 2, and we were trying to divide it by 2x squared plus x plus 1. So just get comfortable with the two different formats, two different ways you're going to see things. You could always check your work. So we could graph, for example, we could put in y equals this, and we could put in y equals this expression and compare our graphs. They should be the same. So that's one way we could check that work. All right, so that's what they've done right here. And notice that the graphs, both equations here, get us the same picture. Okay? All right, we are going to continue. I know it has an assignment written there, but that was for when we had a real short hour. So we're going to keep going. It says an important case of the division algorithm occurs when the divisor is of the form x minus k. All right, so we have a nice linear divisor, and k is just a nice real number. Based on the degree of d of x, right, degree is 1, the remainder would have to have degree 0. It has to be smaller than that, which means it would just be a plain number. Okay, so we have our original polynomial. We're dividing by x minus k. We get our quotient, and then we have a remainder that would just be a plain real number. Okay? If we were to evaluate this expression for k, in other words, we're going to put k in for all of our x's. We have a k here. We end up with k minus k and q of k and our remainder. Okay, so we've just changed all of our x's here to k. Well, k minus k is 0, and 0 times anything is going to be 0. So what we all have left here is just a plain r. In other words, if we evaluate our function for k, and that was the real part of our divisor, we should end up with just a remainder left. Okay? It's called the remainder theorem. It says if a polynomial f of x is divided by x minus k, then we can find the remainder by taking our function f and evaluating it for that k value, whatever number we have here. This enables us to find the remainder of a polynomial when it is divisible by x minus k. All right, so example 2. It says to find the remainder when our function 3x squared plus 7x minus 20 is divided, we've got three different options here, divided by x minus 2. So again, focus on your k value. K is just the 2. So we want to find f of 2. All right, that means we're going to take our polynomial and substitute in a 2 for x. So 3 times 2 squared plus 7 times 2 minus 20. 2 squared would be 4. 4 times 3 is 12. 7 times 2 is 14. 12 plus 14 is 26. Minus 20, we get a remainder of 6. Okay? In other words, if we evaluate f of 2 and get 6, then we could have done the long division and got a remainder of 6. All right, second one, we have x minus 1, but remember it has to be x minus k, so we're going to have to think of that as x minus a negative 1. So we are going to evaluate f of negative 1. Once again, we're going to plug that in for our x. We're going to do our math. We've got 3 minus 7 minus 20, which gets us negative 24. So our remainder would be negative 24. And our last one here. Again, we're going to think of this as x minus negative 4. So we're going to take f of negative 4. Negative 4 squared is 16, times 3 is 48, minus 28 minus 20. This one ends up with a remainder of 0. So why is this important or helpful? If we can find a remainder of 0, like this last one we just did, it means that the factor x minus k divides evenly into our polynomial. So we could have taken this expression, divided it by x plus 4, and we would have ended up with no remainder. It would have divided in evenly. This indicates that k is a solution to that equation equaling 0, and it's an x-intercept of our graph. What we have here, the table represents the answers we just found. It's just another way to think about doing that. If we are evaluating f of k and getting some answer, then k is the x value that we plugged in, and what we get out would be our y value. So we just did putting in -4, and we noticed our y value was 0. So our remainder was 0. When we plugged in, what was our first one? A 2, we got a 6. Okay? When we plugged in a -2, or sorry, a -1, we got a -24. Okay? So just another way to check our remainders. All right, the factor theorem says a polynomial function f of x has a factor of x minus k if and only if f of k is 0. In other words, the remainder must be 0 if it goes in evenly. Okay? So using the ideas of the factor theorem, we can take a new look at example 2. We have a known factor of x plus 4. Okay? All right, so we had 3x squared plus 7x minus 20, right? We evaluated it for -4, and we said it came out nice and no remainder. Which means if we take x plus 4 and divide it into this, it should work out perfectly. All right, focusing on our first term, 3x squared, we divide out an x, we get 3x. 3x times x plus 4 is 3x squared plus 12x, and then we have to subtract. The first term drops out. We have 7 minus 12, or -5x, and bring down our -20. If we take our first term, -5x, divided by an x, we get -5. And multiplying -5 to this x plus 4, we get -5x minus 20. And when we subtract, we have no remainder. So that basically is showing me that I could have used this to factor. 3x squared plus 7x minus 20 would factor into x plus 4 and 3x minus 5. Since our remainder is 0. And we don't ever put that on there. Okay? This process can be quite helpful for polynomials of degree 3 or higher. We can find zeros, factors, and x-intercepts using this division idea. So for a polynomial function f and a real number k, the following statements are equivalent. We can say that if we set our equation equal to 0, then x equals k is a solution. Okay? We say it's a 0 of the function. We say it's an x-intercept of our graph. And then x minus k would have to be a factor. Okay? So x minus k as a factor is a special case. Do you remember another method to find both quotients and remainders without long division? And you would have learned this back in Algebra 2, process called synthetic division. What you see here is just kind of an explanation of why it works, how we go from a long division type question down to what we have here as synthetic division. So if you want to take a few minutes and look through that, you certainly can. I'm just going to go on and review the process of synthetic division. All right, so example 3. It says we're going to divide 2x cubed minus 3x squared minus 5x minus 12 by the divisor x minus 3 using synthetic division. And then we'll write our answer in fraction form. Keep in mind that long division will always work. Synthetic division only works Sometimes. We'll talk about that in a minute. So for synthetic division, we are going to basically remove all of our variables. We just are going to use our coefficients. Make sure you separate them enough that you can actually tell the individual numbers. All right, so I've got a 2, I have a negative 3, I have a negative 5, and I have a negative 12. If I am dividing by x minus 3, my k value is really just the 3, right? It's listed as x minus k. So we're going to put a 3 out front. And then for synthetic division, we always bring down our first number to get us started. And then we multiply these together. Okay? So 3 times 2 is 6. We put that answer up here. And then we add down our column. Okay? So negative 3 plus 6 would get us a 3. And then we just keep repeating that process. So 3 times 3 gives us a 9. We add our column, and we get 4. 3 times 4 is 12. Add our column, and we end up with 0. And what that means is that I have a remainder of 0. And then I'm going to work backwards, thinking of this bottom row of numbers here as being the polynomial answer, right, the quotient. So I have no remainder. This would be my constant term. This would be my x term. And this would be my x squared term. And if you think about it, if you're taking a 2x cubed and you're dividing by an x, the highest power you should get would be an x squared. And that's what we're getting here. So my answer, if I take 2x cubed minus 3x squared minus 5x minus 12 and divide it by x minus 3, I end up with 2x squareds, 3x's, a plain 4, constant 4, and no remainder. Okay? The one thing you should take note of is if you are dividing by x minus 3 in this polynomial, then obviously x cannot be a positive 3 or it would make 0 as our divisor. We can't have that. All right, so obviously we would love to use this shorter method, synthetic division, for all of them. Why can't we? The only time we can use synthetic division is if the divisor is in that form x minus k. Okay, so we're going to do 2 more examples and we'll stop for the day. We have 2 polynomials given. It says use either synthetic or long division to divide p of x by d of x. And we're going to look at our expression again as a polynomial and as a fraction. Okay, so our first one, we are taking this polynomial and dividing by this one. Looking at our divisor x minus 1, since it is in that form of x minus k, we can do synthetic on this one. Okay, so for synthetic again, we take our coefficients of our polynomial. So we have a 1 first, then we have a 4, we have a negative 6, and we have a 1. Notice I didn't have any missing terms. I had x cubes, x squareds, x's, and constants, so I did not need to plug in any zeros. We are dividing by x minus 1, which means my k value out front here is just the 1. Okay, we bring down our first term, we multiply these 2 together, and we write it up there. Then we add down, and we get 5. Multiplying 1 times 5 gives us 5. Adding, we get negative 1. 1 times negative 1 is negative 1. Adding, we get 0. So we have a nice remainder of 0 again. And writing our answer as a polynomial, we would say x cubed plus 4x squared minus 6x plus 1 could be found by taking our answer here times our divisor, right? d of x times q of x. And our remainder here was 0, so we don't have to worry about that. So what I've circled here in blue, this would be 1x squared plus 5x minus 1. And we multiplied by our divisor, x minus 1. So that would be the polynomial format. Okay? In fraction form, that would look like this. We would say x cubed plus 4x squared minus 6x plus 1 divided by x minus 1 equals our quotient, x squared plus 5x minus 1. Okay, I would like you to pause the video and try this next one on your own and then turn it back on and check. One thing to pay attention is in our polynomial we have cubes, but we are missing our squares. So we would need to make sure put a 0 in there. Okay. Also notice that our divisor is not a plain x minus k. There's that 2 in front. So we're going to have to use long division for this one. So go ahead and pause the video and try it on your own, then turn it back on and check. All right, we're taking 2x plus 1, we're dividing into 4x cubed plus no x squareds plus 7x plus 9. All right, again, focus just on the first term of each. 4x cubed divided by 2x would give us 2x squared. 2x squared times our whole divisor, we have 4x cubed plus 2x squared. And we're going to subtract all of that. Our first term drops out. We end up with 0 minus 2, or negative 2x squareds. And we bring down our 7x. Repeating that process, dividing negative 2x squared by 2x gives us negative x. Multiplying, we've got negative 2x squared minus an x, and we're going to subtract. Our first term drops out. We have 7x minus a negative x would be 8x, and then we bring down our last term of 9. And 8x divided by 2x would be 4. 4 times 2x plus 1 would be 8x plus 4. And when we subtract, this time we do have a remainder of 5. So, checking how we would write that. In polynomial form, we would say that 4x cubed plus 7x plus 9 is equal to 2x plus 1 times 2x squared minus x plus 4 plus an extra 5. Okay? In fraction form, we would say our initial polynomial, 4x cubed plus 7x plus 9, being divided by 2x plus 1, gives us our quotient plus the remainder portion, which was 5 trying to be divided by 2x plus 1. It's just too small. All right. So check the agenda slide. I will list the assignment now that we've gone a little further than we did on our short day, and this would be 2.4 day 1.